All right, so for those who were here earlier in the session, you saw my colleague Chris Crowley talk about how to use finite time solutions to the Navier-Stokes equation to infer instantaneous dynamics about turbulent flows. And so in this talk, we're going to really be trying to extend these same solutions to talking about statistics. And so hopefully by the end of this talk, I'll be able to convince you that we can use finite time solutions of the Navier-Stokes equation to actually calculate statistics of turbulent fluid flows. And so what I mean by a dynamical approach to turbulence is one that is firmly grounded in the governing equations. So these approaches typically offer short-term predictions, and they can be used for control even. And opposed to this, there are statistical approaches to turbulence, which offer much longer-term predictions, but they typically rely on assumptions that are not based on first principles and are not even always true. And so what we're trying to do here is really relate these two and actually describe these statistical averages using solutions to the governing equations. And this actually happens quite naturally if you have a system that is ergodic. So if you imagine the set of all states of your system, what ergodicity means is that if you start your system in one state and evolve it in time, it will explore that entire set. And this is a really nice property because when we talk about the expectation value of some observable, let's say A, we typically define it as the mean in time. But when you have a system that's ergodic, you can actually rewrite this integral as an integral over that set of all possible states of the system. And what you pick up is this factor of rho, which is the probability that you see state u in time. And so this function rho is actually pretty hard to calculate in turbulence in really high dimensions, but we can do it in low dimensions. And theory predicts that it's going to be sort of fractal in nature and heavily peaked around certain states known as invariant sets, such as equilibria, traveling waves, periodic orbits, and things such as these, right? And so when we calculate this in low dimensions, we actually see that to be the case. So I'm plotting here for the Hanon map what rho of u looks like. And so it's very fractal in structure and heavily peaked around certain states. And that's a really nice property. We can now approximate this integral over state space as simply a weighted sum over these really important states, right? And this calculation of expectation values as a sum over states should not be that unfamiliar to you. If we think about a noisy quantum system, we typically calculate the expectation value of some observable as a weighted sum over eigenfunctions. I'm not claiming that we have a linear basis for turbulence at all, but I'm showing you this is a very similar sort of process and calculation to what we do in a lot of other fields. I'd like to just define, so I called them invariant sets before, that's the dynamical phrase for them. In turbulence, we call these kind of solutions exact coherent structures, which are the equilibria, periodic orbits, and higher order versions of those. And we have a lot of sort of hopeful results that this should work in fluid turbulence. Back in 2001, Kawahara and Pita were able to show that the statistics of planar Couette flow was well described to within 99% by a single periodic orbit. And so that's a really great result. But they had no need to define what the weights were because they only had to use one solution. Typically, in turbulence, you have to use on the order of 10 to 100 solutions for these statistical sums to converge. And then it becomes really important to know what these weights are for each one of these exact coherent structures. And there are typically two ways of doing that. So there's one that's more theoretical called periodic orbit theory, and you essentially define the weights based on the linear stability of each one of these solutions. Alternatively, there's a more empirical method known as basically treating the turbulence as scattering. And when you do this, you observe the transition weight as turbulence evolves between visiting the neighborhoods of each one of these solutions. And from that transition matrix, you can calculate the stationary measure. And those weights basically describe, from that stationary measure, you describe these weights. And so we're going to be testing both of these weighting schemes in a turbulent fluid flow. And that's going to be the small aspect ratio Taylor-Couette flow. So this is when you confine a fluid between two counter-rotating cylinders, and you can find it above and below by stationary end caps. This is a really great system to work with because it's a closed system, so we can very easily relate experiment to numerics. And it contains a continuous symmetry about the azimuthal direction. And since a lot of engineering applications have continuous symmetries, it's really great for us to fold that in as we do this sort of calculation. So the dominant kind of exact coherent structure that we expect to see in this system is a relative periodic orbit. So that's a solution that if you're in the co-moving frame will look periodic, but if you're standing in the lab watching it, it will be recurring, but it will also drift around the continuous symmetry. And we've converged using Newton 12 of these solutions in this Couette flow. I'm showing you here the energy input and dissipation of turbulence, which is in blue, and the solutions, which are the colored curves, just to show you that these are all embedded in the chaotic set. And I'd also like to really draw your attention here to how different this picture looks, this analysis looks in turbulence versus low-dimensional chaos. So when you're doing this sort of statistical calculation in low-dimensional chaos, like in the Lorentz system, you have hundreds of these solutions. Here in turbulence, it's actually quite hard to converge these, so we only have order 10. And that's going to become very important later as we discuss this. So how does periodic orbit theory calculate these weights? It's going to be an infinite sum, where there's a dominant contribution from the linear stability of the solution itself. And then there's corrections to that, which depend on the pairwise and sort of three-body interactions between periodic orbits. We will only be computing the dominant contribution, Ti over gamma I, but we've also computed it adding in these corrections, and the results are qualitatively similar. I'd like to show you that because the product of the flipping multipliers lambda I should go like e to the period Ti, these weights should get smaller and smaller as the period of the solution gets bigger. So we expect longer orbits to contribute less if we come at it from a periodic orbit theory model. We can also talk about scattering. So as I said, these orbits are embedded in a chaotic set, and we can define neighborhoods of all points that are within some distance delta to these solutions. And then we can look at the transition rates of turbulence between each of these neighborhoods. What you end up finding when you compute the invariant weight of this Markov model is that the weight for solution I is going to be the probability that in time turbulence is in the neighborhood of that solution. So it's, I think, pretty easy to understand and think about. So what do we see when we compare these two different ways of computing weights? First and foremost, they fundamentally disagree within the accuracy of our calculation. You get basically disparate ways, different weights of which orbits are important with these two methods. Second, if we look at these scattering weights, we find that there is actually a positive correlation with the period. So unlike what's considered to be the case from periodic orbit theory, there's not a great linear correlation, there's almost no correlation, but if you were to fit one, you'd find they actually get larger and larger with the period Ti. This is similar to what's seen in the Lorentz system by Chiara. And we also find something that looks rather bleak, bear with me, that the error is actually quite large if we compute the average energy and dissipation using each one of these. The scattering weights actually computes the energy correctly, at least its mean, but we think that that's probably just sort of due to cancellation on either side of this distribution that makes that sort of circumstantially correct. If we look, instead of at the mean, but the actual distribution of dissipation over turbulence and the ECS weighted average, we see that they're fundamentally structurally different. The turbulent distribution is much smoother, and the ECS average doesn't capture the tails very well. I'm sorry, I actually have the names are backwards there, my bad. But like I said, this isn't so bleak as we think. This investigation has allowed us to pin down exactly why this sum isn't converging. And that's because in turbulence, you only have so many solutions, right? O of 10 instead of hundreds. And what that means is that turbulence never comes infinitesimally close to these solutions. And that has two big impacts. If we look at the distribution of energy over turbulence visiting the neighborhood of a solution and just the solution itself, we see that they're fundamentally different. If we were infinitesimally close, the turbulent distribution would limit to that of the ECS. Second, we would expect that turbulence samples the ECS uniformly, but we don't find that. So when we're only making these finitely large visitations of ECS, the ECS becomes sampled non-uniformly, and that has very big sort of consequences on the expectation value of an observable over that ECS. And that actually brings me to sort of our future work, right? So through this investigation, we were able to show that periodic orbit theory weights and scattering weights both seem to fail when put under the rather harsh assumptions of turbulence. And that is due to the fact that they're not sampled uniformly and not sampled closely. But this gives us a great direction forward. Now we know that we have to come up with a novel weighting scheme that takes into account the nonlinear neighborhood of these ECS and takes into account that they're not sampled uniformly. Our group has come up, we hope, with such a novel weighting scheme. We weren't able to quite cross our T's and dot our I's to present it at this DFD, but please keep an eye out for our work in journals and at next DFD to see exactly what weights we're choosing to overcome these problems that we've identified. Thank you.
Yeah. So you said periodic orbit theory weights will not agree with statistical weights in Lorentz system.
Yeah.
Lorentz system.
No, hopefully I didn't say that.
The escape rates of the Lorentz systems are arbitrarily close to zero using cycle averages. How do you reconcile those two results?
Wait, sorry, can you say that again?
In the papers you cited of
Yeah.
there is a convergence of the escape rate of Lorentz system up to 10 to minus 6 using cycle expansions. Okay? So I think that tells you that that's correct.
Yeah, so thank you.
Then your weight comparison becomes a bit suspicious.
So thank you for this question. I was really hoping not to come across as at all bashing the efficacy of periodic orbit theory. I think it works incredibly well, and that's what I was hoping to get by posting this. Like, when you have all of these orbits, that theory does work really well. What I was hoping to get across with this talk is that how do these methods work in practice when applied to turbulence? We have a lot of really harsh assumptions we have to make. We don't have a lot of ECS. And in that limit, it becomes practically difficult to utilize it. And so my goal here with these weights is actually to come up with something that's just like practically relevant when you almost have very few solutions, right?
My question is, how do you think that you're going to make progress in that direction by comparing apples to oranges?
Comparing what to what?
Those weights that you gave there, obviously there has to be something wrong with that comparison.
Yeah, I think it's in case of periodic orbit theory, it's not really a convergent sum in this case. So yeah, they really end up not working in turbulence. Yeah.
It's in the paper that you cited.
Yeah, exactly. So we can't use the weights described by periodic orbit theory in turbulence. Yeah.
Is there a very quick question, or?
Yeah, I mean, I wonder if that what you're just telling us is true if we have very high Reynolds number.
So
I hardly believe that is true.
there's sort of this idea in my understanding that the amount of solutions you need for these sort of calculations to converge should increase with Reynolds number. Because as you increase the Reynolds number, you need more and more and more of these solutions. However, I wish I had more useful from these weights I was talking about. We're basically hoping to overcome that with this novel choice of weights by understanding which ECS is the most important, and even when you have a few, to still have these sums converge without a full library.
Why don't we thank the speaker one more time? And we'll